Okay. So where were we? Okay. So last class, we started talking about um, kind of the basics of, first we started with this weird experiment, quantum weirdness, right? The double slit experiment. And as I said, it has nothing to do with what you need to know for quantum computing, but it's a way to kind of appreciate what's weird. So why do these things happen? Okay. And then we discussed kind of the minimal amount of, let's say, quantum physics or quantum mechanics that you need to know to understand what a quantum computer is, right? And we defined various laws, quantum law one, which was kind of, superpositions, QM law two, and finally QM law three, right? So today, what we'll do is kind of explore implications of these laws, right? So we have three laws, and along with them, I'll introduce one additional device, which is a filter. Okay. And I mean, this new device is not something that we need to build a circuit, but it's helpful for understanding at least the principles of quantum computing. Okay. And then we'll see our first non-trivial task, computational task, where having QM laws gives us a significant advantage over working with traditional, let's say, Newtonian laws. Okay. And then if we have time, we'll go to multi-qubit systems, but I think, we'll basically about have just this much time. All right. Okay. And all right, so let's proceed. Okay, so we had three laws. The first one was if a system can be in one of two possible states, then a state is okay. So anything, essentially a qubit is something which can be in one of two possible states. And then it can also be in a superposition of these two states for every alpha and beta, which can be negative, but the sum of squares adds up to one. You get a potential state, right? And then we had quantum law two, which was this measurement property. Yes, so you can call this the superposition principle. Okay. And the measurement or uncertainty principle kind of says, in some sense, nature, the only way you can find information about a state is through a measurement device. And the measurement devices are very restricted. Right? I can't just say, okay, tell me what alpha and beta are. I cannot measure that. I can, whenever I do this measurement, it changes the state. You cannot measure without changing the state, right? And then you get some one of two possible outcomes with these probabilities. Okay. It's a very restricted mode of interaction. So that's why I'm emphasizing that. And that's very important as well. And lastly, we had okay, we had, let me put it as, what am I doing? 3A, 3B that can rotate by any angle or reflect the state. Okay. So these are devices which can change the state, but they can only change in specific ways, right? So they're not, they're still keeping you in superposition potentially, right? And when you do this change, you don't know what the original state is still. You only know what change you made. Okay, if I ask it to rotate by 45 degrees, I know it's rotated by 45 degrees, but I don't know what the new angle is or what the new state is. I just know that relative to the old one, it is 45 degrees away. Okay, same for reflection. Okay. All right, and we also had 3C, which kind of said is really a corollary of the others, but it's good to have it separately stated in some cases. Okay, we can also measure with respect to other perpendicular vectors, u and v. Yeah. No, right? Because you only know what that you changed until you do a measurement. You don't learn any new information about this. When even when you measure, you only kind of get some information, but not the exact. Does that make sense? For reflection, the angle. So the angle, we only know that I reflect rate about this line. Right, that's it. Okay. If it was here, it would be here. That's it. That's the only information I have. Okay. So it's a little bit like saying, just imagine the state is on a circle, right? And you cannot see where the state is on a circle, but you can rotate the thing. So you rotated it, but you don't know where it is still. You just know that relative to the old position, it has now shifted. And the same thing for reflection. Maybe I can reflect it, but I don't know where it was originally, so I don't know where it is now. Okay. But even with this, it's sort of a, such a limiting way to access any of this device or atoms and so on. Remember, this is enough to build quantum computers, as we will see. Okay. We will extend it to make things simpler, but in principle, this is already enough. Okay. But before going on to define what quantum circuits are, I want to take a slight detour into something which has nothing to do per se with computing, but I think is a very good exercise in understanding the non-trivial power you get, non-trivial computational power that you get from these laws. Okay, it's really a toy problem, but I think it's a fun toy. Okay, so before going there, let me introduce a very sophisticated device, polarizing filters. Okay. So what's a polarizing filter? It's almost like a measurement device, but these are actually much easier to build. Okay, these are the ones that you can get in maybe a dollar store now. Okay, so let's say I have a state like this. Okay, a photon is in some state alpha times 0 plus beta times 1. Now, a polarizer, think of it as we are working with photons. So a polarizing filter is really just a piece of glass Okay. And a horizontal polarizing filter, which I'm going to denote this way. Okay. Is a device which does the following, right? So I have the filter, imagine shooting, very pointed light, like a laser through it. Okay. It's a horizontal polarizing filter. What happens? The net outcome is going to be the following. So it's as if it measures the photon in the HV basis, in the HV device. If the outcome is a 0, then you see a 0. Okay, when you measure with the HV device, you only get 0 or 1, right? So a horizontal polarizing filter is kind of the same. We measure, if it's a 0, the 0 goes through. If the outcome is a 1, then it gets absorbed and converted to heat. Okay, so the photon is no longer there. Makes sense? So I shoot it, it's like as if I did a measurement, and then if it's a 1, it eats it up. If it's a 0, it lets it through. All right? So if I were to write it down formally, like I can say something like this. So what's a polarizing filter? It's a device which does one of these two things. You either get a 0 with probability alpha squared, or you get no photon but some heat with probability beta squared. Okay, does it make sense? Right? So in some sense, it's eating up light, with some probability, and it lets it through. But when it lets it through, it changes the state. It is only going to be in state 0 whenever it lets it through. Okay. And as I said, these are devices which are very easy to come by. Or if you have UV polarizing glasses like sun goggles, they're exactly this. If you ever used a circular polarizer for photography, no? Yes? No one's into photography here? Okay, anyway, I have circular polarizers, and they are exactly this. So they let light through, and essentially half of the time, or whatever probability, they eat it up. Okay, they convert it into heat. So that's why when you look at polarizing lenses, it looks a bit darker outside. Okay. All right. So just as we have a horizontal polarizing filter, let's do some calculations, right? Imagine I send, actually, let's do it this way. Imagine I send a state which is completely like this. What happens? I just get it out all the time, right? So alpha is 1, so nothing really happens. The photon just comes through as it is. Okay? And then this happens with probability 1. Now, what happens if I send 1 through? There will be no light, right? So it will be all heat. Okay? And let's say we're only interested in light, then basically you would get no photon, only heat. Right? And let's do, maybe one more calculation. Let's say I send maybe half times 0 plus half times 1, right? So this was our state, sorry, 1 over square root 2 plus. If I send this across, what happens? I would get 0 with probability half, and I would get heat with probability a half. Okay, right? And the same way, if I do minus, I would get the same thing. Except, yeah, I would get the exact same thing, right? It's only depends on the square, not on whether it's 1 over square root 2 or minus 1 over square root 2. The outcome will look the same. Okay. Any questions about this? All right. Now, here's a cool thing. Just as there is a horizontal polarizing filter, there is also a vertical polarizing filter. Okay. And I'm going to denote it with lines like this. And what does that do? I'm going to take a guess. Suppose I send in a photon in state alpha times 0 plus beta times 1. What should the outcome be? Any guesses? Exactly. So you'll get 1 with probability beta squared and heat otherwise. Okay? Makes sense? All right. Okay, so now here's a question for you. What happens if I chain these things? Let's say I do something like this. Can stack 2 filters, one after the other, and I shoot a laser beam at it. What should happen? What would I get? Any guesses? So the first one only lets through vertically polarized light. So it's eating up all of it. The second one only lets through horizontal polarizing. So what happens at the end? There will be no light, right? So in fact, if you have 2 circular polarizers, if you're taking photography, if you rotate them at a certain angle, you'll see that no light gets through. Okay. And you can also play around with, if you have UV polarizing lenses, just put one on top of the other. At some rotation, you'll see that no light gets through. Okay. So the first one, it's only letting things which are 0, and that also happens with only some probability. But whatever comes through is only in 0, right? Or sorry, 1, and then the other one only in 0. Okay. So you would get nothing here, meaning no light. Okay. Any questions about this? All right. Now, I told you there is horizontal polarizing filter, there's a vertical polarizing filter, and as quirky as quantum mechanics is, it also, once in a while throws us a bone, makes certain things easier, and you can actually build a polarizing filter for any angle that you want. Okay? For example, I can build something which is a 45-degree polarizing filter. Okay. So what happens here, if I send something like this through, what should you see? Any guesses? Again, it's not a trick question. Like, you have, if you extrapolate, what you should see would be? Yeah. Any guesses? You should see something which is only at 45-degree angle, right? Everything else will be eaten up as heat. You would only see the 45-degree one. Okay. So you would see either plus, which is basically, remember, plus was the one which is 45 degrees angle, right? Okay. So technically, what this is doing is measuring in the plus minus one basis if the outcome is a plus, let it through. If the outcome is a minus, converted to heat. Okay. So, you get with some probability and heat otherwise. Okay. So for example, let's say I actually send in state, which is 1 over square root 2 times 0 plus 1 over square root 2 times 1. What would you get? This is exactly the plus state, right? So what would I get? It would just go through all the time. Okay. So to see this, you can think about it this way. So our basis now is plus and minus, right? So this is 1 over square root 2 times 0 minus 1 over square root 2 times 1. Okay. And my input photon is completely perfectly aligned here, right? So I'm measuring in this basis, so the outcome is always plus. So I would just see the same thing as it is. No change. Very good. And what happens if I do something slightly different? Let's say I send in a 0, what happens? Well, 0 is here. Okay. If a measure states 0 in the plus minus basis, I would get both of the outcomes with equal probability. Right? So I need to calculate the projection angle. Okay. So I have right? So the probability that I would see the plus would exactly be, this is 45 degrees, right? Would be 1 over square root 2 whole squared, which is half. And the chance that I would see the other outcome minus would be 1 over square root 2 whole squared, which is again a half. Okay. So if I send this out, I would get state plus with probability half and heat otherwise. Okay. So the rules of, how filters manipulate photons is basically the same as measuring units. The only difference is that when you get the other outcome, it's not let through, but it gets converted to heat. Okay. So you can think of a filtering device as two things. One is the measurement device, and then there's a heat absorber for one kind of state. All right. So far, everything is very simple. And I should say, kind of, it's a weird fact that basically you can manufacture all of these things very easily. Okay. And this has nothing to do with anything logical. It's just something that is given by nature. And that is that if you rotate a horizontal filter by 45 degrees, you get a, let me call this the plus filter. Okay, so I can start with a horizontal polarizing filter. Okay, if you're into photography, you see the circular polarizing filters, you rotate it, then it'll only send light at a certain angle through. Okay, so that's why these are called filters. Basically, they're filtering everything except lights in certain angle to come through. So whatever comes out is only at this particular polarization. Does it make sense? This is important for what we're going to do next. That's what I'm stressing. Okay. Now, already I want to say there's something weird going on with what we saw. So to give an example of that, let's go back to this picture. Right? And let's say, let me change it a little bit. If I actually had a sufficiently dark room and or a powerful laser, we can see it even in class, but I don't have a powerful enough laser because it's difficult to filter out extraneous light. But suppose I take a vertical polarizing filter and then put a horizontal polarizing filter and shoot a powerful laser beam through, right? And imagine the laser, the polarization to begin with is like a random thing. It can be pointing 0, pointing 1, or at a random point on the circle. That's what you'd expect when I'm no control to begin with, right? So what happens? What do you get in the end? Will you see anything at the end? No, right? So there's no light. Okay, so no light through. Because whatever comes through here has to be 1, and about you would expect this to be about 50% intensity, right, on average. So half of the things would be eaten up as heat, half of the things would go through. So the intensity of the beam would be like 50% in the middle, and then when it comes to the second part, just like it eats up everything. Okay, right? But now here's the quantum weirdness. These filters are converting light into heat, right? So if I put two, one after the other, no light goes through. If I add something in the middle, do you expect there to be less light or even more light? Intuitive. less, right? Okay. It kind of makes sense, right? I'm adding extra obstacle in between, right? For it to go through one more filter in between. But imagine I add a 45-degree filter now. So what happens? So in this first filter, eats up half of the light, right? But whatever comes through is exactly in state one. Now for the second filter, it's going to do something too. What does it do? Well, we can go back to this calculation. Let's say I do 1 here. So 1 is this guy, right? So the projection lengths are the same. The projection onto plus would be 1 over square root 2. So you would kind of get the same outcome. You'd get plus with probability half, heat otherwise. Do you agree with that? Okay. So what should happen? I should get, maybe 25% of whatever came through. Like the original thing was you ate up half. I'm eating up another half now. But what is the state of the light going through now? It's all plus, right? Okay. Now this is going through the horizontal filter. So what happens next? About half of that is going to go through, right? We already did that. If I send in a plus through the horizontal filter, it gets through with probability half and gets converted to heat otherwise. Okay. So I should expect, 0 and 12.5% intensity. Okay. So uh, what happened? Did I erase that? Yeah. So the counterintuitive thing is the following, right? Without this additional barrier, I should get no light. Okay. We think of filters as kind of reducing intensity always. If I put these two things, there is no light going through. But I add one more in the middle, suddenly light is going. Okay. So this is again a counterintuitive thing that happens because of the laws of. Make sense? It's easy to follow the calculations, but there's something counterintuitive, right? That I'm adding an additional barrier, but suddenly I'm improving the intensity that goes through. Make sense? So keep this in mind. So basically, we are already seeing some seemingly illogical things, but they're consistent with the basic laws of QM, of quantum mechanics. Okay? All right. So let's play with these filters again. As I said, we're going to study a toy problem which has nothing to do with quantum circuits, but to appreciate that you can do non-trivial computational things with just these basic laws. All right? And this is a very fun thought experiment that was designed by two physicists back in the 60s called the Eliezer-Weidmann bomb. Okay. Now, or the EV bomb. It's a beautiful experiment. And what is the experiment? All right, so there is a evil physicist, a bomber, who built a bomb. Okay. And the bomb is triggered by light. Right. So how is the bomb built? So inside the bomb is or actually let's think of it this way. I shouldn't call it a bomb first. There's a box sitting there. Okay. And inside the box is a horizontal polarizing filter, which is connected to a bomb. How do I draw a bomb? Let's say this is my bomb. Okay. Now, if you send in some light through, what happens? So the bomb is triggered by heat. Okay, it's a bomb, but it's kind of, it's heat sensitive. But the devious physicist converted it to a light sensitive bomb. Okay? It's now tied to a horizontal polarizing. So if I send in light, if it's the outcome of the polarizing filter is a 0, nothing happens. The light goes through because there's no heat. Okay? 0. If the light goes through, light goes through. Otherwise, or kaboom. Okay? So, meaning, so we have a bomb with a heat trigger. Any heat leads to an explosion. Right? And, it's triggered by the things. Okay? And now the challenge for us, the toy problem or the experimental problem is you actually see this bomb. Sorry, not a bomb. You see the box. Okay? It's a dark box. And inside, either there is a bomb or there is no bomb. And you have to tell which is which, ideally without exploding yourself. Okay? So it's a puzzle. So the puzzle is, I'm giving you a box which looks exactly like the same. There is a incoming hole for light, there's an outgoing hole, right? Either it's a bomb or a dud. Okay? And dud means it's an empty box. Whatever light you send through, it just goes straight through. You can't look inside the box. The only way you can access it is to shoot a photon through it. Okay? So we are given a box and our goal is to detect if it's a bomb or a dud. Okay. Ideally, as I said, obviously you can shoot it. If it explodes, then you know it is a bomb, but that's not a good outcome, right? So you want to do this while minimizing the chance of an explosion. Okay. Any questions about the setup? So this is the puzzle we're going to solve. Try and solve. Yeah. Yeah. You know, if it's a bomb, it's tied to a horizontal filter. That much you know. You can think of a version where it's you don't even know that there is some filter, but right now, let's say we do know it's a horizontal filter. Okay.
And the dot also.
That has nothing. That has nothing. Again, you can consider a version where it has a horizontal filter, but no bomb attached to it. But right now, I think that's almost impossible to tell unless you explore. But this one, let's see what happens. Either there is this entire apparatus of this piece, you either have this whole thing or you don't have the whole thing. Okay. And as I said, this box is sitting in front of you. You can do whatever you want. If you tamper with it, it explodes. And you have to figure out if there is a bomb inside or it's a dud while minimizing the chance of explosion. Okay. So, let's come up with some ideas and see what happens. So let me draw a kind of a picture. Okay, so you see this box, and we have to figure out if it's a bomb or not. All right. And any suggestions on what we might try? We have access to all the filters that we want. We went to a dollar store, bought zillions of filters, and we also have lasers. So what do we do with these things? How can I? Well, let's get started. Let's see what happens. I want to detect if it's a bomb or not. So what can I do? Any suggestions? So the first attempt I'll write down. It's going to be useless, but I think, it's good. So let's say I pass, I have a laser, so I'm just going to pass it through a horizontal polarizing filter. Okay. And then I send it through the box. So whatever comes out of the polarizing filter is going to be 0. It has to be horizontally polarized. Okay. And if I send this light through, what happens? Kind of there are two cases. If bomb, do I learn any information about the box in this case? No. Right. So if bomb, we see 0 on the other side. If dud, also we see 0 on the other side. Okay. So we learned no information about the box, but it, at least did not explode. Right? Okay. So what else can I try? Any guesses, sessions? We want, let's say for now, I want some non-trivial chance that I will detect that it's a bomb without exploding. Yeah, okay, let's try. So attempt 2 is the way to send plus is of course to just put the 45-degree polarizing filter. So whatever comes through, we know is going to be plus, right? So this is one way we can control what sort of filter you're sending through, what sort of light you're sending through. Okay, so now what happens? If a dud, we see plus on the other side. Okay, we're not done yet in the sense that we need to recognize what this is too, right? On the other hand, if it's a bomb, what happens? If a bomb, we see 0 with probability half, or we explode with probability half. Okay. So, I mean, 0 and plus, we can distinguish with another filter. For example, if I put a vertical filter, then it will give me some advantage in telling those two. Right? So, now let's make sure we can, do the further processing too. And so imagine you gave me this device. I'm just going to do the following. Okay, I put a vertical filter through and then check what happens. Okay, so then we have two cases. If a dud, then we see light with probability half, right? And if a bomb, we see no light with probability half, we see or an explosion. Right? So meaning if I shoot a very powerful laser through, then lots of photons through like this, I would be able to detect, I have some chance of detecting it's a bomb. With probability half, I'll detect it's a bomb, but with probability half, I will explode. Right? So I have some, chance of detecting it's a bomb without exploding, but it's just like half. It's a pretty high risk to take to detect something as a bomb. Make sense? Okay. Can I do anything else? Any suggestions? How can I, can I try something else here? To improve the chance that I will detect it's a bomb while decreasing my odds of an explosion. Yeah? Okay, that's an excellent suggestion. So let's try that. Right, so intuitively that should help us reduce the chance of an explosion while creating some difference. Okay, right? So let's go back to this picture. Okay, so here my photon is at a slight angle to 0, right? So for example, let's say I choose my photon to be something like this. This is 0. And I choose like, let's say this one, which is 1 degree, let's say, just to make up a number, which is small. Okay. So meaning I'm putting a filter which is slightly off horizontal. Okay. This is like 1 degree polarizing filter. Right. So then all of the incoming light is like it's cosine 1 degree times 0 plus sine 1 degree times 1. Okay. So this is the, what I'm sending through, and what happens in the end. I would see, if a DUD whatever comes through will just be psi again, nothing changes, right? And if a bomb, we will see 0 with probability cosine 1 degree squared, and an explosion with probability sine of 1 degree squared. Right? And sine of 1 degree is a very small number. It's like, maybe 1 over 100 or something. So 1 over 100 squared is a tiny. Much better than. Okay. But there is a problem. How do you tell which of these two you're in? Remember, we can't just look at a state, right? You don't know what state it is in until you do a measurement. So we reduce the chance of an explosion, and the state is different, in one case and the other. But how do we know which state it is in? The only way is to make another measurement afterward. Right? So this experiment, as I described, is not complete. You sent a light through. Until we measure, we don't know what was the outcome of the experiment. Right? So let's fix that. How can I fix the I need to do another measurement. So what should I do here? Any suggestions? I need to do some post-processing. I did some input. Now I got some output. I need to check something. I can do, a couple of things, but let's say, what should I do? Any suggestions? There are many options. So maybe I will put let's say I put a horizontal filter again. Okay, the only things I have are this filter, so let me play around with them. Right? So what happens now? So this is the experiment I'm doing. You gave me the box. I'm going to put a 1 degree filter first and a horizontal filter in the end and see what happens. Okay. So this is the setup, experimental setup. Okay, and I send a photon through. So let's do a couple of calculations. Oops. And I'm going to break it up into 2 cases just so that we have things easier. The DUD case is usually the simplest, so let me do that. If the box was a DUD, whatever I sent in just comes out as it is. Okay, so I would get the same psi. Okay, and what do I get finally? I would get 0 with probability cosine 1 squared and heat with probability sine 1 squared. Okay. And all right, on the other hand, if a bomb, what happens? The setup is the same, but what comes out here if it's a bomb? We either explode, and if we don't explode, it's always 0, right? Okay, so meaning we either explode. This happens with probability sine 1 squared. Okay, or we just have a 0. Okay, so in this case, you have a 0 with probability cosine 1 whole squared, more or less, and explosion with probability sine 1 whole squared. Is this a useful experiment then? I would say not, right? Because the final state is 0 with some probability, or you explode it. So essentially, you will only learn it's a bomb if you explode it. Okay? And now I can, so we should change the experiment, right? So any suggestions on how to change the experiment? Again, let's just keep shooting darts and see what happens, right? So what would be the next natural thing to try? Let's say I put a vertical filter here. Okay. And then what happens? So this is my experiment modification. Okay, so I change the experiment this way. I change what I'm doing at the very end. Okay. It makes sense, right? Because somehow I want to distinguish between 0 versus 1, right? If it's always 0, then I would never see light. Okay. So what can I do now? We can do the same sort of calculations again. So if a dud, what happens? Whatever comes here will be exactly the same state. Right? And then what comes afterward will be 1 with probability sine 1 whole squared and heat otherwise. Okay? Right? On the other hand, if a bomb, then what I see is, if there is no explosion, it has to be a 0. Right? So with probability cosine 1 whole squared or an explosion. Okay? All right. Now, what does this mean? I'm when I send in the vertical thing, it's just going to eat it up, right? Completely converted to heat. So I will just see heat with probability cosine 1 whole squared, or I would see an explosion with probability sine 1 whole squared. Okay, so the chance of an explosion is similarly small, and you can potentially detect it, right? So in both cases, if there's a heat, there's heat, you can't tell which case you were in. But if you see a light, then you know it was a dud. It makes sense? So I set up this experiment, you gave me the box, I put a 1 degree filter in front, I put a vertical filter, and I say, okay, was there light at the end? If there is a light, I know that it was a dud. Okay? If there is no light, then I don't know. Make sense? So what did we gain? Meaning we can detect it's a bomb with probability roughly sine 1 whole square. Okay? And chance or risk of an explosion is also sine 1 whole square. Okay? And if you work it out numerically, this is basically 4 times 10 to the minus 6, roughly. Okay? So we have a tiny chance of explosion, which is good for us, but we also have a tiny chance of making any progress. Right? So in comparison, when we did the first attempt, or attempt 2, when we sent in plus, we had 50% chance that we would actually detect it, but we also had a much higher chance of an explosion. Right? So kind of, you improved one but hurt the other. The ideal would be the chance that you detect it's a bomb is like 90%. The chance that you explode is like 10%. Right? So right now, either I'm getting both to be small or both to be big. Right? Make sense? Okay. So now the question is that the best you can do? So challenge. Can we get the best of both worlds? Chance we detect a bomb is close to 0.9. Chance we explode is less than or equal to 0.1. These are just made up numbers. Ideally, I would want to do this for any two numbers which are in my favor. Can I do 99% and 1%? Right now, we don't even know how to do 1/3 and 1/3. We seem to be stuck at basically the same number for both. Okay. Any questions about the setup? Yeah.
Shouldn't it be chance that the
Well, when I say when we chance we detect, it's basically like whether we can tell them apart, let's say. Okay. You're right in how we phrase it. If it's a bomb, what happens? Let's make sure. If it is, where do we go? Yeah. If a dud, then we would see light. And if it's a bomb, we would see only heat. Yeah, so if you're right, we're detecting if it's a dud, but I think we can flip things around and get the same outcome as well, right? So instead of sending 1 degree, I could send 1 degree from the, no, that would make the explosion. But anyway, so we'll see how to fix this anyway, okay? But you're right, we're basically saying I can detect it's a dud, right? So it's safe to use with this probability. Okay. Or in some sense, I can tell them apart with some probability. That's it. I gave you 2 devices. You want to see which is which. Then I can tell them apart with probability 4 times 10 to the minus 6, which is really tiny. But on the other hand, it's not too maybe destructive because my chance of explosion is also small. Right? In the other case, we had half and half, where we had a higher probability of telling them apart, but my chance of an explosion was much higher. Okay? Yeah.
So if I want to figure out if the box is a dud, then I'm going to have to keep sending a photon until I see light. But if it's a bomb, that will never happen, right? So won't I have an explosion with probability 100%? Because I will keep sending in photons. Because if I want to be certain that it's a dud, I'll have to keep sending it in until I see.
Intuitively, yes, but no. You can do a better experiment. Yeah, we'll see. That's why, quantum mechanics is weird. Okay. It seems like basically what you're saying, I totally agree with you. Intuitively, it seems like there's no wind to be had here, right? So how can you detect it's a bomb without actually exploding? Everything you do seems to hurt either your chance of explosion or your chance of detection. In some sense, it's very counterintuitive, right? How can you detect if you're not exploding? Otherwise, if you're not kind of triggering the other case at all, how are you even able to tell them apart? Okay. But here's the punchline. I'll first tell you the punchline, and then we'll work towards figuring it out. There is a way to do an experiment where we can detect with probability 1. Okay? Imagine I give you 2 devices. I will be able to tell they are apart. If I don't explode, I will have 100% confidence that, which is which. Okay? Detect with probability 1 if we don't explode. Okay, I mean, this is meaningless. I can design an experiment very easily. I'll just shoot a 1 photon at it. Then I will explode in the bomb case with 100% probability. If I don't explode, then I know for sure that it's not a bomb, right? But it's only when you couple with the next one, which is chance of an explosion. Is 0.1. Okay, so I can design an experiment where the chance that I explode is 10%. And in fact, I can make it 0.01 also at the expense of, the experiment taking a little bit long. Right? And you can do this only with the laws of quantum mechanics. If you don't have quantum mechanics, then you cannot. If you're only allowed states which are like alpha times 0 plus beta times 1, where the numbers are positive, then you cannot do it. You have to use negative numbers. Okay, does the statement make sense and why it should be mysterious? Basically, we're saying I can design an experiment where the chance of an explosion is as small as possible. I can make it 0.1, I can make it 0.01. And when I don't explode, that is all of the other time, I will know exactly whether or not it's a dud or a bomb. Okay, makes sense? Any questions? So if I give you a dud, you will never explode. If you give me a bomb, I'll explode with probability 0.1 and I will know it is a bomb the rest of the time. Okay, so that's what we are heading for. Any questions about the statement? No? It is kind of funny. It is strange, right? That you can do this. Should be very mysterious. Anyway, so the actual way to do this is surprisingly simple, but very clever. Okay. And I should say, it's not just, I said it's a toy problem, but there's a very famous quantum algorithm called Grover's algorithm for search. And the basis for that is the same principle that we're going to exploit. Okay, and it'll come up in a second. So the experiment I'm going to do is very similar. I'm going to do this 1 degree thing. Because I definitely don't want to shoot something which has a very high angle with 0, because then, I'll explode. Just terrible. Right? Okay. So what I'm going to do instead is the following. I'm going to shoot this through. All right. And instead of measuring immediately, I'm going to recycle this photon. Make sense? So I shoot a photon, it goes to the thing that comes through, I'm going to send it back. That's it. And I'm going to do this some number of times. Some n times. We'll decide what n is in a second. Okay. I do this loop n times, and then after that, I'm going to do something else. What is that something else? I'm actually going to put a 1 here. Put a vertical polarizer at the very end. Okay, so the algorithm is, recycle or resend the photon if no explosion, obviously. N times. And after that, put a vertical polarizing filter. Okay. All right, that's the experiment. And, the setup is there. The cleverness is kind of done. Now we just have to do some tedious, or let's say somewhat tedious calculations for the two cases. So what happens if it's a bomb? What happens if it's a dud? Work out all cases and see if there is a difference in the outcomes. Okay. So for example, if it is a dud, what happens? That's the easiest case to work out. So let's do that first. So if it's a dud, what comes out? The state is exactly the same. Right? It goes back, comes through. Again, when I send the same state to the same filter, nothing changes. So you're just looping through the same thing, nothing happens. What comes out here is exactly the same. Okay. So the final outcome would be either, heat with probability cosine 1 whole squared and light with tiny probability. Okay, we can change the thing to also, make further modifications if you want. And actually, you know what? Let me make one change to the attempt. The previous one also works, but I want to simplify the calculations a little bit. So here, I'm going to say rotate by 1 degrees device. Okay, instead of putting a 1 degree polarizer, that just changes my calculations, makes them a little messy because it might get absorbed as heat unwantedly. So I'm just going to change it to say, make it a rotate by 1 degree device. Okay. And I'm going to initially send just a 0 through. Okay. Any questions? Kind of the same thing. I'm just doing it this way. I think the calculations are a little bit easier. The earlier one was more intuitive. You're just recapturing it. The point of recapturing is to use the memory of the system, right? You have the same device that you're running through. Okay, so we are trying to exploit that. Okay, and so here I'm using 3A, which tells me that there is a device to rotate by 1 degree. Okay. Okay. So this is my new experiment, and let's see what happens with this. So if the first case, again, the easier case is if a bomb, so if a dud. Okay. So what happens if it's a dud? The first time I send it through, it gets rotated by 1 degree. Okay, so you get something like this, and it just goes straight through. What happens the second time? It gets rotated by 1 more degree, right? So continuously, what happens? So each time the photon goes through, my angle increases by 1 degree, right? So I rotate by 1 degree, but the box is done. There's nothing happening in there. It's just going straight through, comes in, gets rotated by 1 degree, goes straight through, gets rotated by 1 degree, and so on. Okay. So we repeat it n times. And after n times, the final state is what? Now I start from 0. Then the first time I remove by 1 degree, and then by 1 degree, then by 1 degree, and so on. Okay. So I'm going to set n to be exactly 90. Right? So if I do it by exactly 90, then my final thing final state is exactly here. Right? After n times, the final state is at an angle of n degrees. Okay, I'm going to choose n to be 90, so which is 90 degrees. So the final state is 1. Okay, so what does this mean? And I'm passing it in the end, after looping it through n times, I'm passing it through the vertical polarizing filter. Okay, so in summary, oops. So summary, if a dud, we should see light all the time. Make sense? You know, if it's a dud, what I would see light all the time. Okay. Any questions? So there's no, ambiguity here. If it's a dud, the light will eventually appear. Okay. So now let's do the other calculation, which is a bit more involved, but not too much. So if a bomb okay, so what happens? We're kind of doing the same thing, right? Except now this is the setup, right? So I'm shooting this photon through, rotate by 1 degree, send it through the box. It comes back or it explodes, if it exploded, it exploded. But if it comes back, it gets rotated by 1 degree again and so on. Okay. So what's the outcome? And there's some chance we explode. Okay, let's put that aside for now. We will calculate it. But let's say we somehow got lucky and we did not explode. Then what happens? So if it did not explode, what comes out here? 0. Right? So it goes back in, gets rotated by 1 degree. If it did not explode, 0 comes again. Right? So polarizing filter has this strange resetting property. If you did not explode, you're 0. If you did not explode, you're 0. If you did not explode, you're 0, and so on. Okay, makes sense? All right. Okay, so if it did not explode, what should we see here? There's some chance I might explode. We have to figure that out. And, I haven't said anything about that. But if there is no explosion, what's the end outcome? Will I see light ever? No, right? So either we are exploded or there is no light. Right? Because, if I didn't explode, no matter how many times I do it, the only thing that comes out is a 0, but I'm putting it through a vertical polarizing filter, so there would be no light. Okay? So now we need to calculate what is the chance we explode. Okay? If it did not explode, we win, which is something that we could have gotten anyway. So that's not the big win here. The big win should be with the odds of explosion. Okay? All right. So how can I calculate that? Initializations and how I might calculate the chance of an explosion? Well, let's do it one step at a time. In the first round, what's the chance of an explosion? Well, I rotated by cos 1 degrees, like 1 degree. So I have cos 1 times 0 plus sine 1 times 1. So what's the chance that I explode? Sine 1 squared, right? We kind of figured this out already, right? This was one of the first attempts that we tried. We said, I'm going to minimize the chance of an explosion. So I'm setting it a slight angle. I would have exploded with probability sine 1 whole square, right? And if I did not explode, what's the chance for the second round? Any guesses? Let's say I did not explode in the first round. What are the odds for the second round? Same thing, right? So it's getting reset every time. You either exploded, then you're lost. But if you did not explode, it's getting reset every time, right? So I come back as a 0 here, and 0 gets rotated by 1 degree, and then the same thing again, right? So this is chance of an explosion is sine 1 whole square. Okay, so I keep doing this, 90 rounds. So overall, my chance of an explosion is sine 1 whole square. Okay, so each round, the chance of an explosion is at most sine 1 whole square, right? And I'm doing this 90 times. So what's the total chance? So the total chance of an explosion is at most 90 times this probability, right? So imagine, I say I'm going to toss a coin 90 times. If it ever comes up head, you're dead, right? And the chance of a head is small. It's only sine 1 whole square. The first time it appears is, so the first, the chance that you die in the first round is sine 1 whole square. The chance that you die in the second round is sine 2 whole, sine 1 whole squared again, and so on, right? So the total chance that you would die is at most 90 times the chance that you would die in a single round. At most. You can also come up with an exact bound, but we don't need an exact bound for now. Yeah? Oh, sine 1. No, it's not multiplicative, right? So basically, if I die once, then I'm dead. I don't have to die every time. Make sense?
Shouldn't you calculate the probability that you survive?
Exactly. If I want the exact number, then I would do that. I'm just getting an upper bound here. But if I really wanted the probability, then this is equal to 1 minus sine 1 whole squared to the power 90, 1 minus this. Okay. So the chance that I would die is 1 minus the chance that I don't die. But that means that I shouldn't die in every round. Okay, I think maybe this is what you were asking for. This is what you would get. So I should live every round. The chance that I live in a single round is 1 minus sine 1 whole square. So basically cosine 1 whole square. I should live in every round. So 90 times sine to the power 90 and 1 minus. Okay. But if you work it out, this is always true. 1 minus p to the n is at most p times n. Okay. You can also come at this in a more intuitive way by saying, I'm tossing a coin 90 times. The chance that I would ever get a head is, like 90 times sine 1 at most. Okay. And this is good enough for us. So what is this number? This is 90 times 4 times 10 to the minus 6, which is basically 36 times 10 to the minus 5, which is 0.00036. So what happened here? So magically, we have an experiment where the total chance of explosion is very tiny. Okay, and if it did not explode, we know for sure what case we are in. Because if it's a dud, we'll always see light. If it's a bomb, we will never see light. Okay, so let's summarize. If a dud, we will see light. If a bomb, no light, with probability 1 minus, whatever this number is, and explosion with probability less than or equal to 0.0036. It's quite remarkable, right? So in some sense, we did it 90 times, looped it 90 times, and then suddenly we had this huge success. And we will explode with some probability, that is unavoidable, but it's a tiny probability. And whenever we don't explode, we know for sure what case we. Does it make sense? So where did the magic come from? What do you think? So how did this magic happen? Intuitively. Again, it's a rotation, but still, this is. So what about quantum did we use here? So sorry. Mm, that is true, but actually, if you do the calculations, there's something very, very numerical. There's a numerical wonder that happens. Okay, and the wonder is really that. So, what is sine 1? Right, that is like 1 over 2 pi, right? 1 over 360 degrees. Okay, so this is basically like 1 over 360. Okay, and the win comes from the fact that if it was 90 times sine 1, we wouldn't get any advantage. It's 90 times sine 1 squared. Okay, so this is hard to grasp, and it is very mysterious, but the win comes from the fact that the probability is squared. Okay, so the way we did it, I fixed the angle first, and then I said I did it 90 times. Right? So imagine, on the other hand, I fix the number of times to do, the number of repetitions, n. Okay, maybe I'll set n to be 1,000. Okay, and what angle should I pick? So basically, if I want this to work, I need to pick an angle so that after n rotations, I get exactly 90 degrees. Okay, so I would choose epsilon to be something like n over 4, like pi over 4n. Okay. So like, sine of pi over 4 is like sine 90 degrees. There's a difference between degrees and radians, right? So I have to use this. So I would rotate by angle, which is like, pi over 4 times n many, degrees or radians. Okay. Or 1 over n degrees, basically. Right? Or 1 over n degrees. Right? Or sorry, 90 over n degrees. Okay. 90 is basically pi over 4, right? In radian notation. Okay. And the win comes from the fact that the probability of explosion is sine of epsilon whole square. Okay. So this is sine of 90 over n degrees whole square. Okay. Which you can compute, and it turns out to be some constant by n squared. So this is the square that's giving us the advantage. If it was not a square, but somehow it was like absolute alpha plus absolute beta, you would not get this. Okay? The fact that the probabilities are squared is where the non-trivial stuff happens in quantum. And in fact, almost all special algorithms which give us a quantum advantage exploit this fact. If it was only n times c over n, it's still a constant. You're not going close to 0, right? It's n times c over n squared. So if I do it, 1,000 times, I would get even better probability and so on. Does it make sense? Intuitively, again, it's kind of hard to grasp why this is happening, but we did the math. Everything checks out. We did not cheat anywhere, except we followed the laws to their logical conclusions. Yeah.
So is it always better to have as large as possible, even though you're doing the cycle more and more times? Perhaps doing the cycles.
Yeah, it increases. Again, that's also mysterious, right? You're using the box more and more, but you're getting more confidence, which is also mysterious, right? So you think, okay, I'm trying to detect there's a bomb inside. I'm doing it more and more times, but how is it giving me a win? It should be increasing my chance of detection, yeah, but it should also increase the chance of explosion, right? But the win comes from the fact that one is, changing at a much faster rate than the other. Okay. And you can actually quantify, like, the way it shows up in algorithms is, imagine every time you want to trigger the box, I charge you $1. And you can show that this is the best trade-off you can get. If you have X amount of dollars, the best advantage you can get is something like 1 over X. The chance of explosion is like 1 over X. And if you don't explode, you will know exactly which case you're in. That's more non-trivial, but there are results which also talk about that. And none of these would be possible if you don't have quantum mechanical laws. The square in the probabilities is where all of the magic is hidden. Okay. Any other questions? I would encourage you to, it is counterintuitive. So just play around, see if there is no other way to cheat. Like, is there any other experiment I can do which can detect this? It's good to try other things which fail, and somehow this one thing works really nicely. Okay. All right. So, this is to give, I think, the only algorithm, it's also an algorithmic question in some sense, right? I said, imagine you get charged $1 for every time you use the box. You want to minimize the number of dollars. This is before detecting it's a bomb, and this is one way to do it. Okay. And it clearly shows an advantage of quantum mechanical computation or laws where you can use it to your advantage, right? And so when we come back, we will just talk about how to design quantum computers, but we won't have time to see what advantages it can give over classical algorithms. Okay. This is one sort of quote unquote computational advantage. It's like a toy problem where we are seeing an advantage. But if you would like to know more, there's something called Grover's search. It's a very deep algorithm, very influential algorithm. It's quite complicated to understand. But I would say the core of that algorithm is, again, the same principle that one of the probabilities will be like sine squared. So it goes as 1 over n squared, and you're doing it n times, so you get a boost. Okay. And if you're really into it, there's a beautiful series of videos on 3 Blue, 1 Brown, which talks about this algorithm. Okay, but as I said, we won't have time to cover it. All right. Okay. So let me stop here. And when we come back on Monday, we'll start talking about more definitions of how do you actually build a quantum circuit? How do you formalize it? And we'll see maybe one other toy example of a quantum advantage, but this I would say is the main one. Okay.